Let's start. So, hello, welcome to the graphics programming virtual meetup. And today we will talking about BVH. I think this is a relatively long chapter. Yeah, let's see. Yeah, BVH is like object subdivision. I guess everyone knows the basics because we talk about BVH so much. Basically, yeah, we have a bunch of primitives they store in the leaves, and then we build a tree on top of it where each node stores a bounding box, and then the parent node stores a bigger bounding box. And then when we have an array, if this array does not intersect with a bounding box, then anything inside it we just don't need to check. One property of primitive subdivision is that each primitive appears in the hierarchy only once. Yeah, this is not a property for some other structures such as oct tree, but yeah, with spatial subdivision is not the case. Yeah, another implication is that memory needed is bounded. We can pre-allocate array basically. It's just need that size. BVH are more efficient to build than KD trees and are generally more numerically robust and less prone to miss the intersection due to round-off errors than KD trees. So it's a default for PBRT. Also, a lot of researches goes into BVH. Don't I don't think much about PET trees these days. So the constructor of this BVH aggregate class takes enum that describes which algorithm used to partition primitives to build a tree. Default use surface area heuristic. And alternative is, what is this? Which can be constructed more efficiently and more easily parallelized, but does not build trees that are efficient as surface area heuristic. Remaining two approaches use less computation but create fairly low quality trees. So three stages of BH construction. First, bounding information about each primitive is computed and stored in an array. Next, the tree is built using the algorithm encoded in the split method. And the result is a binary tree, which is not necessarily the case for BVH, but I guess for the PBRT code base, they just always use binary trees. And finally, the trees convert to a more compact and more efficient pointerless representation. So they use pointers when, I guess, just pointers and malloc when they build a tree, and then afterward they compact it into an array. The implementation is easier with this approach. Yeah, I can see that versus computing the pointless representation directly. Which primitive be stored in the BVH? An instance of BVH primitive structure store its complete bounding box and its indices. So this is basically just an index, just having an index and also a bound. And they calculate the centroid on the fly. I've also seen other code bases that store centroid and size, which is also possible. And the hierarchy construction can now begin. In addition to initializing the pointer to the root node of the BVH, an important side effect of the tree construction process is that a new array of primitives is stored in ordered primitives. This array stores a primitive ordered so that the primitive in each leaf node occupy contiguous range. Oh, I see. It is swapped with the original primitive array after tree construction. So memory for the initial BVH is allocated using allocator. They're all based on CPAPA's monotonic buffer resource, which is basically an arena allocator. Using malloc, use 10% more memory and take approximately 10% longer. That's some good number. Yeah, but this dumb allocator can't be used concurrently from multiple threads, so they have one copy for each thread with the help of this thread local class. I remember being confused that they have a thread local class, but in some part of their code base, they also use a CPAPA thread local keyword. So, but it seems this is just more powerful. It can have operation like iterating through all the thread local variables, stuff like that. And if the HLBVH is selected, then we use this build HLBVH. Otherwise, we build recursively. Initial call to this function pass all the primitives. Which returns a pointer to the root of BVH for the primitive they are given, which is represented with the BVH built node structure and the total number of node created is stored in the total node. Yeah. This value is atomic, so it can be run in parallel. Each BVH build node represents a node of the BVH. All nodes store a bond 3D, bond 3F, which represent the bond of all children beneath the node. Each interior node store pointer to the two children in, yeah. Interior node also record the coordinate axis along which primitive were partitioned. This information is used for improve the performance of the traversal algorithm. Interesting. I don't know about that. Leaf nodes record which primitive or primitives are stored in them. The elements of the primitive array from the offset first prim offset up, but not including yeah, I guess this is a typical thing. This is why the primitives array need to be reordered so that this representation can be used rather than store a like state vector for each leaf node, which would be horrible. We call it BVH build node because this is not the final product. It's the intermediate representation. And they distinguish between leaf and interior node by whether their child pointers have value null pointer or not. Leaf have null pointer children, and the interior has, yeah. And build recursive also take a pointer total nodes that used to track the total number of BVH nodes have been created. And this value make it possible to allocate exactly the right number, yeah, of nodes. The ordered primitive array is used to store primitive references. Primitives are stored in leaf nodes of the tree. It's initially allocated with enough entries to store all the primitives. Though all entries are null pointer, and when a leaf node is created, build recursive will claim enough entry in the array for its primitives. Ordered primitive offsets start from 0 and keep track of where the next free entry is, and it's atomic. So yeah, multiple thread can modify it. And when the tree construction is finished, the primitive is replaced with the ordered primitive array. if VH primitive only has a single primitive, then the recursion has bottomed out, and yeah, a leaf node is created. Otherwise, it partitions elements using one of the partition algorithms and reorders the array elements so that they represent a partition subset. So if I guess if the bounds are so close by, like the surface area is 0, then they also create a leaf node. All the primitives are just there are only one primitive, then they create leaf node. Otherwise, they create the partition. And they compute the primitive bounds because it's needed regardless interior or leaf node. So then this is just a for loop. At leaf nodes, the primitive overlapping the leaves are appended to the ordered primitives array. Yeah, because the offset is atomic, so multiple threads can safely perform this operation concurrently. This is just performing a copy of primitives to ordered primitives, and then the initialized leaves. For interior nodes, a collection of primitives must be partitioned between two children's subtrees. Given m primitives, there are in general 2 over m minus 1 minus 2 possible ways to partition them. Yeah. But in general, when building PVH, we first consider partition along a coordinate axis, meaning that there are about 3n candidate partitions along each axis. They select the axis with largest extent of bounding box centroid. Yeah, this is a simplistic method. An alternative would be try partitioning the primitives along all three axes and select one that gives the best result. But yeah, that's very costly. So they use a simplistic method. This approach gives good partitions in many scenes. Yeah, they choose the axis which the extent of centroid is largest. Like in here, x is from here to here, definitely smaller than y, so they will partition with y. General goals is to select a partition of primitives that does not have too much overlap of the bounding boxes. Yeah, substantial overlap means we need to traverse both children's subtree. This idea of finding effective primitive partition will be made more rigorous when we discuss SAH. But now let's just see what's going on here. So they calculate the bound of the centroid. And again, if all the centroid points at the same location, then they just create a leaf node. None of the splitting method works well for that's a really weird case. The primitives are otherwise partitioned using the choosing method. Yeah, basically at here. The true recursive calls access independent data other than when they allocate space in the ordered primitives array by incrementing ordered primitive offsets. Therefore, when there are a reasonable large number of active primitives, those calls can be performed in parallel. Yeah, that makes sense. So, okay, so I guess they are smart enough to say reasonable large number of active primitives, because if it's small, then doing it spawning a thread would just be horrible. So yeah, but for reasonable large size, they use a parallel for the PBRT implementation of parallel for the current thread will handle the first recursive call, while another thread, if available, takes the second. And it will wait for all the loop iterations that have completed. So it's fork and join. And the code for the non-parallel case is the same, just without parallel for loop. We also didn't include the code fragment partition primitive based on split method. Here it's just use the value of split method to determine which primitive partition scheme to use. These schemes will be described in the following. Simple split method is middle, which first computes the midpoint of the centroid along the splitting axis. And they use the primitive are classified in two sets depending on whether they're centroid above or below the midpoint. And they do it with CPAPA's standard. So the partition partition and the partition based on whether the centroid at a specific dimension is less than the midpoint. And equal count is just even simpler, just partition primitive into equally sized subsets. First half, yeah, but while this approach can sometimes works well in case of this, it can works very poorly when when in this and this, we just partition them. Oh, this is a midpoint. Yeah, midpoint has the same kind of issue. Again, they use STL and element. I do feel like this kind of stuff, like nth element and partition, are the best part of STL, maybe. And yeah, I feel like if I remember correctly, this is retracing in one we can use, just very simplistic method, but yeah, not very efficient. And SAH. So most of the best current algorithm for building acceleration data structures for retracing are based on surface area heuristic, which provides well-grounded cost model for answering questions like which of the number of partition of primitives will lead to a better BVH for reprimitive intersection test, or which of a number of possible positions to split space in a spatial subdivision scheme will lead to a better acceleration data structure. So SAH model estimates the computational expense of performing retracing tests, including the time spending traversing node of the tree and time spending of intersection tests. And the algorithm for building acceleration structures can then follow the goal of minimizing the cost. And typically, a greedy algorithm is used to minimize the cost for each single node of the hierarchy being built individually. So for the surface area heuristics, the idea is that for any point in building acceleration data structure, we can create a leaf node. And in that case, any ray intersection will have the cost of this, which is like the intersection of each individual primitive, and we just add all of them together. And the other option is to split the region. In that case, the cost will be the cost of traversing uh, the current node, and then the cost of intersection with the children times the probability of going to A, it's going to children A, and then the same for children B. The choice of how primitives are partitioned affects the values of two probability as well as the set of primitive on each side of split. Yeah, I feel like I feel like this was when I got what surface area heuristic is this diagram. Is that basically surface area heuristic saying is that for an arbitrary ray, its probability of intersect with a box is proportional to the surface area. So the probability of a ray, if a ray intersects with A, and then the probability of the ray intersect with B is like the surface area of B divided by surface area of A. Yeah, this is just the math formulation of that. And when split method has a value of SAH, the SAH is used for building a BVH. And that's just tautology. I think partition of primitives along the chosen axis that give a minimum SAH cost estimate is found by considering a number of candidates partitions. Yeah, this is a default because it creates most efficient hierarchies for retraversal. Once it has refined down to two primitives, then the implementation switch over to directly partition them in half. Yeah. Yeah, two primitives just directly. They still use nth element. I thought they would just use some like dumb comparison. But yeah. Rather than exhaustively considering all the 2n possible partitions along the axis, computing the surface area for each to select the best. The implementation here instead of divides the range along the axis into small number of buckets of, oh yeah, remember that binning? That's what this article was about. Yeah, just because, yeah, this is just way too expensive. And still we can get nearly as efficient as a result using this kind of buckets. We found that 12 packets usually works well in practice. An improvement is to make it adaptive, but they didn't do that. And for each primitive, the following fragment determines the bucket that it centrally lies in and updates the bucket bounds to include the primitive bounds. And then for each bucket, we have a count of number of primitives and the bound of all their respective bounding box. Then we use the surface area heuristic to estimate the cost of splitting at each of the bucket boundaries. The fragment below loop over all the bucket and where is the fragment below? I think it's here. And the number of split is bucket -1. And we have a cost. Yep. We set the estimated intersection cost to 1, estimate traversal cost to 1/2. Absolute amount of computation necessary for node traversal array bounding box intersection much less than the intersection array with a shape. The full cost of shape intersection test is even higher. But they intentionally underestimate the performance ratio because the raw amount of computation each performed does not measure their full expense. With lower traversal costs, the result BVH would be deeper and require more nodes. Yeah, that's use more memory, which is undesirable. And they find this build a good BH, and yeah, that's why it's called a heuristic. In order to choose a split in linear time, the implementation first perform a forward scan over the bucket, then the backward scan over the bucket that incrementally compute each bucket's cost. Previous version of PBRT used ON square algorithm, yeah, which is not good. So bound below, we calculate the bound and they calculate the count and then the cost, the forward scan. And then they do a backward scan for the cost above. And yeah, and then given all the costs, the linear search of the potential split find the minimal cost and which bucket to split. The final surface area heuristic cost for a split, we need to divide by surface area of the overall bounding box to compute the probability PA and PB before adding the estimated traversal cost we have. Yeah, we just add 1/2 and also divide by the surface area. And then the partition to reorder nodes in the BVH primitive array according to the where the bucket is. Yeah, but if they find the cost is too high, they just create a leaf node. Maybe we should stop here. I feel like LBVH, this is cool, but we talked about something similar before, so yeah. Maybe we can stop at here because it's getting a bit long.
Works for me.
Yeah.